Hello, everyone. My name is Meng. I'm really excited to be here to present our work, Hydro, Surrogate-Based Hyperparameter Tuning Service in Data Centers. This is the joint work with Qinghao, Zhisheng, Qiaoling, Peng, Yonggang, and Tianwei from Nanyang Technological University, Shanghai AI Lab, Peking University, National University of Singapore, and SenseTime. Let me begin with some background of hyperparameter tuning. To train a deep learning model, like ResNet and GPT, users are required to predefine a hyperparameter recipe, encompassing essential elements such as the learning rate, batch size, weight decay, as well as specific arguments related to the optimizer and learning rate scheduler. To obtain better model performance, users try many configurations and find the best one. Hyperparameter tuning is important. For example, PyTorch released an updated version of their facial model weights using a well-tuned training recipe. Compared with the previous ResNet 50 version, it obtains a significant 4.8% accuracy improvement and even outperformed the larger model, ResNet 152. However, over the past few years, the size of the popular language models are exponentially growing. Performing a hyperparameter sweep on such large models is too expensive. Consequently, hyperparameters of most large models are not well-tuned and can lead to subpar performance. On the other hand, tuning jobs are prevalent and consume substantial resources. For instance, Microsoft reports 90% of models require tuning and tests 75 trials in median. And Alibaba also indicates that 65% of jobs repeatedly run over 5 times. However, GPUs are significantly underutilized. Only 16% and 35% of GPUs achieved higher than 50% GPU utilization in Alibaba and Shanghai AI Lab, respectively. And Vector Institute also reports their average GPU utilization of tuning jobs is only 15%. To solve these challenges, we propose Hydro, a holistic system that optimizes tuning workloads in both the job level and data center level. And we first introduced Hydro Tuner. It automatically generates surrogate models by applying transfer theory and model fusion. The key mechanism of Hydro Tuner is surrogate-based tuning. Different from existing tuning systems, which search on the target model directly, Hydro first scales down the target model and creates a smaller surrogate model, whose model weight is reduced for hyperparameter tuning. Then Hydro searches on the surrogate model and transfers the best hyperparameter back. The major concern is that, can hyperparameters be transferred? Here we take a 2-layer transformer model as an example. The original model weight is 4096, and we sweep different learning rates and record the converged training loss in this figure and highlight their best learning rate. We scale down the model weight by 2, then the new model weight is 2048. And we continuously apply larger scaling ratio, S equals 4, S equals 8, and S equals 16. Here, the model weight is only 256. We observe that the best learning rate shifts across the model scales. However, applying Hydro on the same transformer model, we obtain consistent best learning rates across model scales. Additionally, Hydro obtains lower training loss. This is partially because Hydro allows much higher learning rate compared with common training approaches. The magic of Hydro derives from its underlying theory, which is called maximum update parameterization. We call it mu parameterization for short. It is the theoretical work that enables maximum feature learning for infinite-width neural networks. We use a one hidden layer MLP model to illustrate how mu parameterization works. The model has a scalar input, infinite-width hidden layer weight U, and output layer weight V, and we use SGD optimizer with learning rate 1. In common practice, we initialize the model based on the normal distribution and apply the same learning rate to each layer. However, MU parameterization fine-grained adjustment model initialization and learning rate. This can avoid upper layer blow-up and obtain feature learning. For better understanding, we summarize some intuitive insights here. Mu parameterization theoretically achieves maximum feature learning for the infinite width neural networks. Its practical impact is that it enables hyperparameter transfer across model scales. For a set of models with different weights, we correspond them to the infinite width limit. Then we can obtain the benefits of applying mu parameterization. It solves the unbalanced training issue via layer-wise learning rate adjustment. It also ensures consistent magnitude updates for each layer during training regardless of its weights. However, this problem is that manually implementing mu parameterization is burdensome and error-prone. Any mistake may incur hyperparameter transfer failure. Our system automatically applies the novel hyperparameter transfer theory together with multiple system techniques to jointly improve the training efficiency. For a target model, Hydro first traces the model with torch fx and scales the model by user-defined model scaling ratio s. Then Hydro applies mu parameterization to the surrogate model for different layers, like the input layer, hidden layer, and output layer, as well as different optimizers including STD and ADAM. Hydro follows specific rules to automatically adjust them. Based on the model scaling, Hydro delivers significant benefits. We use a wide ResNet 15 model as an example. We observe that the G-flops is directly proportional to the reciprocal of S squared. This means that when applying the scaling ratio 8, we can receive 64 times G-flops reduction. Furthermore, we can also obtain roughly 8 times GPU memory reduction simultaneously. However, for some small models like ResNet 18, the 8 times model scaling only provides less than 10% acceleration. This is mainly because GPU is underutilized, and model scaling further exacerbates this issue. Consequently, Hydro further enables inter- and intra-trial fusion to improve the hardware efficiency. The inter-trial fusion combines multiple models into a single entity, and intra-trial fusion subsequently performs compiler-based optimization. The inter-trial fusion technique derives from HFTA, and Hydro further extends its application scope and optimizes the fusion process. In the general training process, we create several trials with different hyperparameters. These trials have identical data and model architecture. The only difference is their optimizer configurations. So we can leverage their similarity and batch multiple trials into a single one by fusing their operators. Hydro binds surrogate models automatically and implement the optimizers to support both the model fusion and parameterization simultaneously. We illustrate the impact of integrating model scaling and inter-trial fusion techniques on ResNet 18 using the A100. The x-axis is the trial fusion number, and the y-axis is their accumulated throughput. We can see that Hydro obtains over 20 times speedup and allocates over 600 trials on a single GPU. In contrast, utilizing inter-trial fusion alone yields only marginal enhancements compared to MPS. And next, Qiaoling will introduce more about the Hydro coordinator.
Hi, I'm Qiaoling. Let me introduce the data center aspect of Hydro. In data center level, we design Hydro coordinator to leverage idle bubbles resources of pre-training job while interleaving training. With the rapid popularity of foundation models like GPT-4 in recent years, some large language model pre-training workloads exist in data centers. These large language model pre-training jobs typically require substantial long-term resource allocation. As a result, tuning jobs often encounter resource scarcities and significant delays in training. And we have identified an opportunity for tuning jobs to leverage the resources allocated to large language model pre-training jobs. These resources are typically vast, often requiring hundreds to thousands of GPUs. Moreover, pipeline parallelism is commonly applied but inherently introduces bubbles. For example, we depict a popular pipeline schedule, one forward, one backward, with 4 pipeline stages. It is obvious that a large amount of resources are wasted because of bubbles. On the other hand, each bubble has different activation memory requirements and cause unbalanced memory footprint issues. This further exacerbates hardware inefficiency. And our solution is to leverage bubble resource through interleaving hydro trails with LLM pre-training job. Hydro adaptively resume and pause tuning trail during the bubble stages. The fine-game self-stand resume control eliminates the performance interference caused by CUDA kernel running simultaneously. And besides, we can dynamically adjust the trail fusion count according to the remaining GPU memory. And hydro trails are perfectly suitable for the bubble interleaving execution due to the following unique features. The first is throughput insensitive. Unlike general deep learning training job, tuning jobs are more tolerant of slowdown or partial trails. The second is the deterministic and scaled model memory footprint. Based on model scaling, the scaled model has much smaller memory footprint than the original model, and we can profile their memory consumption to mitigate the potential out-of-memory issues. Besides, trails can adjust the fusion number to fit the remaining memories, and we can selectively disregard the GPUs that have rich capacities. To illustrate the effect of hydro coordinator, we first depict the single GPU SM activities of a GPT model with 4 pipeline stages. We can clearly observe 2 complete iterations comprising both forward and backward stages. And there exist large bubbles during their intervals, and the SM activity is extremely poor during the bubble. We interleave hydro trail with this LLM pre-training job. They can utilize the bubble stage and achieve a relatively high SM activities at about 15% with no evidence slowdown to the GPT model training. In this figure, the hydro trail fills 16 ResNet 18 models and obtains around 15% of the exclusive throughput. Now let's move on to the evaluation part. We first give an intuitive experiment to validate the effect of surrogate-based tuning over multiple dimensional hyperparameters. We randomly select 10 configurations labeled as A to J, and consisting of batch size, learning rate, and momentum settings for the ResNet 18 model. And we visualize the hyperparameter transfer effects across different scaling ratios as equal to 1, 4, 1, 2, 4, 8. Since the tuning job is essentially a ranking problem of hyperparameter configuration, we mainly care about whether the order is maintained, especially for the top configuration. And from the result, it is obvious that the hyperparameter ranking transfers well across different scaling ratios. We further conduct an end-to-end experiments across 6 popular workloads, covering language modeling and image classification tasks. From the table, we can see that Hydro substantially outperforms state-of-the-art system retune by 8 to 78 times in time reduction, while obtaining better final model qualities. As a summary, in job level, Hydro enables joint optimization of theory and system techniques, and in data center level, Hydro identifies and leverages idle bubble resource of pre-training jobs. And our code is open source. Please check GitHub website if you are interested. Thanks for your listening.